All right, you guys, this one's on sorry, I said that loud. Probability rules. My students said this is not online, so I'm putting this on. I should have done this a couple of years ago, so I'm a little behind on this lesson. So, which of the following is a method for improving accuracy of a sample? So, it's the one that uses larger sample size. That's what always improves the accuracy of a sample. So, look for the one for larger sample size. So choice C right there. Okay. All right, so probability rules, you guys. So the rules on probability of A, and the probability of A is written like this, the probability of A, so P with the parentheses A. There's a couple things, you guys. It's in between 0 and 1. It could be 0, it could be 1. It's just some decimal. Okay, I'm going to show you how to get the fraction answer, and we just convert the fraction to a decimal, top divided by bottom. Okay, and this is how you do it, you guys. So the book gives a weird, to me, it's an awkward one. I'm showing you how I taught it when I used to teach 8th grade. Probability of A is your top, your numerator is your number of favorable outcomes, the ones you're looking for. The denominator is your total number of outcomes. Okay, and if your sample space is S, then the probability that you pick something in that sample space is 1. That means 100%. So for example, say I'm picking somebody out of my AP statistics class. What's the probability I pick somebody out of that class? Well, it's 1. It's 100%. Okay, that's what the 100% means right there. All right, and the complement rule, this is pretty slick once you get the hang of the complement rule, you guys. So it's written with A with a little C right there. The probability of your complement is just 1 minus the probability of A. So the complement of A is just 1 minus the probability of A, okay? Because because they add up. So say for example, the probability of picking a boy student out of my class is 60%. So the probability, the complement of picking a girl would be 1 minus 60% or 40%. They have to add up to 100%. So they're complements of each other. They add up to 100%. And that says right there, sorry, that's in the way. It says, note the probability of A is just 1 minus the complement. So the probability of picking a girl would be 1 minus the probability of picking a boy. And the probability of picking a boy is 1 minus the probability of picking a girl. Okay? So if A and B have no outcomes in common, then they are said to be mutually exclusive. So here's a Venn diagram right here. Like for example, you know, my AP statistics class, I only have boys or girls. There's no in-betweens in there. There's no outcomes in common. So they're said to be mutually exclusive. And so the probability of picking a boy or a girl, or a probability of picking A or B, is just the probability of A plus the probability of B. Okay, and typically in any math class, you see the word or, that means addition right there. Okay. All right, and then so here's a Venn diagram that shows your sample space. There's my sample space right there. And then, so I'm going to just separate it up, and this side is my A right here, so this side's going to be my complement of A, okay? They're mutually exclusive, so here's all my boys on this side, here's all my girls on this side, okay? Boys and girls are an easy example. Okay, and this means union, you guys. This sort of U sort of upside down thing without the leg right there. This is like the probability of A in union with its complement is the entire sample space, which equals 1 right there. Okay, so the probability of picking A or the complement of A is equal to 1. Okay, and then when it's an upside down U like that, it's said to be intersection, you guys. And so up here, these guys don't overlap at all, so there is no intersection. So A intersection, its complement, is that this is called the empty set. So I have that written down right there. So that symbol is the empty set. In math, these funny brackets are called set notation brackets, and so there's nothing in there. It's empty. It's an empty set right there. Okay. All right, so the marital status of young women. Okay, so here's an example in our book. So let me get this out of the way so we can see what's going on here. So draw a number at ages 25 to 34 years old at random and record her marital status. At random means that we give every such woman the same chance to be the one chosen. Okay, that is, if we choose an SRS of size 1, then they all have the same chance of being chosen right there. So the probability of any marital status is just the proportion of all women ages 25 to 34 who have that status. And if we drew many women, this is the proportion we would get. And so this is just a study that somebody did. So here's the probabilities that they've never been married. That they've been married is 62%, 62.2%. Well, the reason why there's not very many that have been widowed is because of the age factor right here, okay? So the widowed is 0.005, and then divorced is 0.075 or 0.075, sorry. So there it is right there. So each probability is between 0 and 1. You see how these are in between 0 and 1 right here? And these probabilities all add up to 1 because the outcome together gives me the whole sample space of my marital status for my women ages 25 to 34. So the probability that a woman that we draw is not married, we can use the complement rule. The complement rule is we take the married, okay, and so the opposite of that would be not married, okay, so we do 1 minus this right here, and we get 37.8% right there. So the complement rule is great. So that is, if 62.2% are married, then the remaining 37.8% would not be married. So never married and divorced are considered disjoint events because you can never be married and then divorce at the same time. That can't mix. They don't mix. You can't get divorced unless you've been married. So if you've never been married, then you've never been divorced. That's all that says right there, okay? All right, what else do I have here? So the probability of married or divorced would be, the probability of never married or divorced, since they are mutually exclusive, we find the probability of never married and the probability of divorced, okay, and you add them together and you get 37.3% or 0.373, okay. So that is 37.3% of women of this age group are either never married or divorced, okay. All right, so rolling some dice probabilities. So this figure right here is going to display this 36 different possible outcomes of rolling 2 dice. So what's the probability we should assign to these outcomes right here, okay? So there's all the 36 ways right there. So let's see, how'd it go right here? How'd they do it? They did a little bit different than me, than I would have done it on the board. You can get a 1 on the first dice, a 1 on the second dice, a 2 on the first dice, a 1 on the second dice, a 3 on the first dice, a 1 on the second dice, a 4 and a 1, a 5 and a 1, and a 6 and a 1. So there's all the different ways I can roll a 1 on the second dice and the 6 different ways on the first dice. Here's rolling a 2 on the second dice in the 6 different ways, and then 3s, and then 4s, and then 5s, and so on. There's 36 different ways. So that would be my bottom number right there. Okay, so casino dice are carefully made. Their spots are not hollowed out, because if they were hollowed out, they would be different weights. And so so they are filled with a white plastic that have the same density as the colored plastic of the bodies. So for casino dice, it's reasonable to assign the same probabilities to each of the 36 outcomes, okay? And because all 36 outcomes together must have a probability of 1, then each outcome must be 1/36. So the probability of getting a 3 and a 3, there's only one of these chances right here out of the 36. So 1 out of 36, okay? We'll get some more into that in just a second. So gamblers are often interested in the sum of the pips on the up faces. So the pips are just the numbers that you see that are upside. So what is the probability of rolling a 5? Okay. All right, so the probability of rolling a 5 would be this. Your bottom number is 36 because there's 36 different ways right there. And you go count the ones of rolling a 5. I can get a 4 and a 1. I can get a 3 and a 2. I can get a 2 on the first dice, a 3 on the second, and I get a 1 on the first dice and a 4 on the second. So there's 4 different ways I can get roll a sum of 5 right there. Okay, so it's 136, 136, 136, 136, or you can just do, there's 4 ways out of 36, so 4 out of 36 is 1/9, you guys. It reduces to 1/9, but our textbook likes to do decimal answers, so 4 divided by 36 is 0.111. So it's 1 divided by 9, okay? All right, so what about the probability of rolling a 7? Okay, let's see, did I put that figure there? Let me go back here. So the probability of rolling a 7, let me go back here. Let me go back to a bigger picture right here. So here's the bigger picture. So the probability of rolling a 7, there's 36 ways, and how many ways can I roll a 7? There's 1, there's 1, there's 1, so there's 3, there's 1, there's 1, there's 1. There's 6 different ways, so it's 6 out of 36, which reduces to 1/6, okay? So keep in mind, you guys, getting a 5 on the first dice and a 2 on the second dice is different than getting a 2 on the first dice and a 5 on the second dice. So there are 6 different ways, so 6 out of 36 would be 1/6 right there. And 1/6 is 0.167, okay, 6 out of 36. All right. So Benford's Law talks about taxes. So fake numbers in tax return payment records and invoice expenses Account claims and many other settings often display patterns that aren't present in legitimate records. So some patterns, like too many round numbers, are obvious and easily avoided by a clever crook. Others are more subtle. So it's more striking fact that the first digit of the numbers in a legitimate record often follow this distribution that's called Benford's Law. So the first digit, it can never be 0. So, you know, think about tax returns and say you made $52,000. Okay, the first digit would be the 5 for the 52. Well, they're saying that the first digit on tax returns, the probability that the first digit is 1 is 3. I'm at school, so you hear these announcements, sorry. Is these. So here's the probabilities for the first digits on tax returns. Sorry about that, you guys. So Benford's Law applies this to the first digit of the sizes. Okay, let me get going here. So consider these events. A to be the first digit is 1, and B to be the first digit is greater than 6. Okay, so what's the probability that the first digit is 1? Well, it's that right there. Probability that the first digit is greater than 6 is the 6 or 7 or 8 or 9, and you add them all up and you get about 22.2%. So the probability that your first digit is 1 is going to be greater than the probability that your first digit is either one of those 4 digits right there. Okay, that's what that says. So the probability that the first digit is anything other than 1 can be done using the complement rule. Okay, so 1 minus that, so 0.699. Okay, so the events of A and B are disjoint, so the probability that the first digit is either 1 or 6 or greater. Disjoint means they can't overlap, so you can either get a 1 or a 6 or greater would be the addition of those two numbers right there. Okay, so be careful to apply the addition rule only to disjoint events. We'll show you what to do on when they're not disjoint in the next lesson right here. Okay, so the probability that you pick an odd digit, you just add up all those odd probabilities for the odds, and it should get you to 0.609. Okay, all right, so let's see. So let me go. Okay, so random digits. Okay, now we're out of Benford's Law, you guys. If I just randomly assign the digits 1 through 9, each digit, if I picked one of those, say I put them in a hat, you guys, and I said pick one of those numbers at random, what's the probability I get this number right here? Well, there's 1/6 out of 9 numbers, so it would be 1/9. The probability of picking any one of these numbers is 1/9. So it is not like Benford's Law. So the probability that the first digit is 1 or 2 or 3 or 4 or 5 or any of them, they're all 1/9 right here. So it's not like Benford's Law on tax returns. So what's the probability of picking a number 6 or greater if you're just randomly picking digits? Okay, and it wasn't a tax return or something right there. It's going to be 1/9 plus 1/9 plus 1/9 plus 1/9. There's 4 of them, so 4/9, and then 4/9, of course, is 0.444. You do 4 divided by 9 in your calculator. Okay, so compare that with Benford's Law, and they're a little bit different right there. Okay, all right, if you're in my class, that would be your homework assignment. Take care, you guys. Sorry for the long assignment.